Oh gosh, okay, hello everyone. Welcome back to Comp 3430 Operating Systems. Despite what my voice currently sounds like, I am feeling like 1,000 times better than I have been in the last few days. I appreciate your patience with the class cancellation on Wednesday. Like I thought about doing this remotely, but you know, I was having trouble even just like reading little stories to my kids. So like, it's kind of like, nah, I'm not even gonna bother trying. So I appreciate your patience with that, with the short notice and everything. What I want to do first is I want to point at what we're going to do next week, and then I want to get into today's stuff. And today's stuff, what I want to do is spend some time taking a look at both a minor description of what we're looking at with VSFS and inodes and indirect blocks, specifically indirect blocks, because they don't really do an excellent job of describing this in the textbook. So I want to visualize this idea so we have a good sense of what this actually looks like. And then what I want to do is I want to move to a real file system. The real file system that I want to take a look at today is ext2. And ext2 is a much older file system, but in terms of similarity to what we're familiar with VSFS, there's not a huge leap to try and figure out how ext2 works compared to VSFS. So we already have some visual sense of what an ext2 volume looks like just from the diagrams that we saw in the textbook. So what I want to do is like mechanically step through, here's a binary file. I want to find all these different parts in the binary file by looking at it in my terminal, and I want to spend some time doing this in C. I want to be able to traverse the file system's image with C code, because next week what we're going to do is take a look at exfat, which there is a bit of a bigger leap in terms of the structure of the file system. And ultimately the goal is for you to be able to do the same kinds of things with exfat as what we're doing in class today with VSFS and ext2. So first things first, I want to pop over here to the course resources and to the course schedule. And what I want to take a look at is the week 3, file systems consistency and redundancy. So we're not quite finished file system implementation stuff. We lost a class, so we're going to have to catch up a little bit next week. But what we're going to move into is file systems consistency and redundancy. And the overall idea with this is, I mean, file systems are probably one of the most important parts of an operating system in terms of like maintaining your data. You don't want to lose data on your file system. That's the key idea that we have with this stuff. So there's 2 approaches that we're going to be looking at here to try and make sure that we don't lose data, and to try and make sure that if our system crashes, our file system and our operating system can still come back up again after they crash. The first one is called RAID, and this is a hardware approach. And this is from chapter 38. And then the other one is called FISC, which is like checking the file system after you crashed to see if you can figure out if there's anything wrong with it and then try to fix it. And then journaling, which is like a preventative approach. Rather than just you know, try to deal with it after the fact, try to prevent getting into an inconsistent state in the first place. What I want to be really clear about with chapter 38 in particular is that there's a lot of stuff in here that has like formulas and calculations for the performance characteristics of a physical hard drive. And I want to be 100% clear that I don't care about that stuff. I really do not care about that stuff. I don't want you to have to spend 1,000,000 hours memorizing these formulas. They're not relevant. They're not important to me. If you want to figure this out, you'd open a textbook and like look up the formula. That's not a valuable thing to me. What I really want you to get from this chapter is this learning outcome right here and this learning outcome right here. Choose an appropriate RAID level given requirements or given a workload. I'm going to describe a situation to you like these are the needs that I have as a person who wants to build a RAID array. Which one should I pick? Which RAID level should I pick for that? Or alternatively, here's two RAID levels. Tell me what's different about them, about the three major characteristics. So like overall performance, reliability, and then the third thing that I cannot think of right now on the top of my head. There's three properties that we'll be looking at there. So yeah, don't worry about the hardware, like the formula-based performance characteristics of these drives. I don't care. I really, really don't care. Just thinking about like relative performance of the different RAID levels for these chapters. All right, so that's where we're going to go next week, but the earliest that we're going to see this stuff is on Wednesday, because on Monday I want to spend time with exFAT stuff. So we'll be finishing up stuff from this week on Monday next week. So with that, what I want you to be able to do is kind of the same things as the thing that we were doing on Monday. I want you to be able to describe the data structures used to represent files and directories as seen in Unix. So this idea of inodes today specifically, that's what I'm thinking about here. I want you to be able to describe how a specific file system is implemented. This is ext2 today. And I want you to be able to show how common file operations are performed in terms of manipulating a file system's data structures. So what I want to do with this today is like literally look at the data structures, but like binary, hex. I'm not going to look at binary. We're going to be looking at hex values, but like I want to step through all the data structures that are actually in a file system in terms of like looking up the contents of a file. That's what I want us to be able to do today. So for this part, I want to take a look at this, this overall structure of VSFS, and then really specifically this idea of an inode. So I'm going to pop over here to my tablet. And what I'm going to kind of do is describe what I've got on the screen here right now. This is just a high-level description of that VSFS that I've kind of transcribed. So we've got this superblock structure here up in the corner. And then beside that, we've got these allocation structures. So the two bitmaps that represent whether or not an inode is used and whether or not a data block is used in the data region of this thing. Right beside the allocation structures, we've got this inode table right here. And the inode table is the part that I really want to focus on right now in terms of looking at an individual inode and the metadata that it has. We looked at this a little bit on Monday in terms of looking at the output of that ls command, and we saw that there's stuff like special permissions that each file or folder has. There's properties like when it was created, who it's owned by, how much disk space it actually takes up. And so there's lots of stuff here that's going to be like that, but I don't actually care too much about that because that's a lot of like straightforward metadata that makes sense to keep track of for a file in a file system. The part that I really want to take a look at here are these two right here, the direct block pointers and the indirect block pointers. This is how our inode actually refers to the data that's in the data region. So these are going to be references to the data region that actually contain the data for this file. The direct block pointers are pointers. They're going to be references that will literally refer to an entire block's worth of data. So what I'm going to say here is that my direct block pointer area for this inode has two direct block pointers. In the textbook and with ext2, we're looking at more like 16 direct block pointers, but just for the sake of illustration, let's just say we've got two direct block pointers. The direct block pointers that we have for this are basically going to be an array of integers. So these are numbers that refer to the blocks in the data region. And what I'm going to say is that this file has two blocks that are direct block pointers, blocks 1 and 2. And so what that says is that the first block for this file, or the first data for this file, can be found way up here in block 1. And if this were like a C program, what we'd find at the very first byte of this data block is something like $include. So literally the actual source code for the data that we've got here. Block pointer 2 is going to be the same thing, the continuation of the data that's in this file. So like for loop, conditional statement, variable declaration, there's just going to be more source code here as data in this block. But now let's say that we've written a C program that's bigger than 2 blocks in size. So 1 block on this file system is 4096 bytes in size, or 4 kilobytes. This is an insanely big C program. Let's say that it's 16 kilobytes in size, which is, I don't know, I wouldn't want to write a 16 kilobyte size file. Please don't write 16 kilobyte size files, but let's just pretend that this is happening right now. The indirect block pointers kind of look the same way here. I'm going to say for us right now that we have 2 indirect block pointers, but I'm only going to fill in one of them. The first indirect block pointer, I'm going to say points at block number 3. What this says is if I follow block number 3 here, up here, what I'm going to find in this data block is not data. It's not actual source code anymore. It's going to be a whole series of block pointers, direct block pointers. So let's say, for example, that I've got one indirect block pointer and it's going to point at 2 or 3 more blocks. So my indirect block pointer here might have something like 6, 7, 8. And this is basically saying that if I follow this indirect block pointer up to block number 3, data block number 3, the very first entry here says go to block number 6, and that's where the next data is. So in block number 6 here, there's going to be a bunch of stuff that continues with the C program that we've got. So if we've got, I don't know, what's good C programming stuff? Pragma. And then, gosh, I don't know. I don't program in C anymore. We don't put segfault. We'll put the word null. So there's more C code here. And then in block 7, there's more C code. That's the next thing that this indirect block pointer points at. So basically what we've got here is that each of these indirect block pointers now just points at another block worth of information that represents this file. The authors kind of go about saying that most of the time we never actually, I'll get to you in just a second, most of the time we never actually get to these indirect block pointers because most files are small. Most files are going to be small enough that they fit within the direct set of block pointers, but there are files that, you know, we've done a Blu-ray rip and we want to put it on our drive. We need to go to something that's much, much bigger than is able to be accessed by the direct block pointers. Yeah? So the data that we have in each of these blocks is going to be a total of like 4K chunks of the original data file that you've got. So I'm going to draw some art here. I'm going to draw a picture here of my cat. So this is Walter, this is my cat. The way that we're going to put all of this data into this file system is by putting it all in as like 4 kilobyte chunks. So what that kind of means, I'm going to pretend that each of these actual squares on my screen here is a 4 kilobyte chunk. So that's going to kind of mean that the bits here for this one will get put into this block. The bits here for this one might get put into this block. The bits here for this one might get put into this block here. They're not necessarily right next to each other, but it's just going to be the binary data for that specific chunk of that file. We're not going to break it up into squares like this. It's more of that linear array of bytes that we kind of think about. but each part of that file is going to get scattered across all these different blocks. Ideally, we want them to be all right next to each other, but in practice, it's not going to happen that way all the time. Does that answer your question? Okay, awesome. Yeah?
Each block is reserved specifically for a single file, right?
Each block is reserved specifically for a single file, yes. Yeah, so any block that you have will only be allocated to one file. Yeah, so that's a really good question. The question is basically, can we just make a bunch of mostly empty files and then basically steal a bunch of space? Absolutely, yes. This is something that's called internal fragmentation, where what we're doing is, if I make a bunch of plain text files that have just a single period in them, that single period is 1 byte, but I have to take a whole 4K block to represent that 1 byte. I could fill up an entire file system's worth of inodes with these 1 byte files and then not be able to do anything else with the file system, even though technically there might be terabytes of free space on the file system. Yeah. So that means that there could potentially be lots of wasted space if you have lots of really, really small files. We'll touch back on this later when we're looking at exFAT, when we're looking at the cluster sizes of that, because it's a similar sort of idea. But that's a great point. Thank you. Yeah.
I'm guessing there's a trade-off, like accessing different blocks is more expensive than just accessing a single block, right? So then there's a trade-off having to, like you can't just make all the blocks like super small. That way you don't have that empty space.
So the question is, can I just could we make the block size really small and then not have all that empty space? And the answer is, yeah, you could, but then your block size is really small and doing reads from the hard drive is going to be slower. Drives like SSDs and spinning hard drives are optimized for certain sizes of transfers to happen. And when a transfer is going to be, like you're making something that's a request that's much, much smaller than the optimal transfer size, it's going to slow things down a lot. Alternatively, to read even small files, then you may have to request many blocks as opposed to just 1 block like you would have been able to do before. But it's a trade-off. It's a trade-off. Yeah?
Instead of setting a constant size for a block like 4 kilobytes, can we instead use delimiters to specify a block? This way, smaller files would need a smaller block if we can like specify the beginning of a block and the end of a block.
So the question is, can we specify like basically a block size per file? Is that kind of what you're thinking? Okay, so can we put delimiters in the file system? That's a great idea. So like put basically comma separated file, put a comma in to say like this is the end of the file. You can start a new block here. Yeah, that's also a really good idea, but it's going to lead to a lot of really expensive calculations in terms of figuring out where the file actually ends. With this approach, you can always assume that a file will either be taking an entire block or some partial block. You're never going to have to figure out where a file starts. It will always start at the beginning of a block. You don't have to try to find that block start location. So it's more of a trade-off of like, we're going to waste a little bit of space, but we can always guarantee that these calculations to figure out what file start is going to be pretty fast. Yeah.
Doing that would also make it so you can't easily extend the file as well, right? Like you'd have to make
yeah. So that's a good point. If we try to make the file bigger, then it's going to make it difficult to make the file bigger because we're going to have to like recopy the entire file somewhere else and then make it bigger after that. Making files bigger in general is also just a difficult problem, as we're going to see, because with this idea of these blocks don't necessarily sit right next to each other, that's going to become a problem as we try to add more things or delete things or make a lot of small files and delete some of those small files and then insert more data into it. This is external fragmentation, and this is where there's maybe lots of blank space that we have in between things, but there's not enough contiguous free space for us to put something. And the idea of these fixed size blocks tries to help with that idea. If we can always guarantee that there's a block free and we can just put blocks in wherever we want, then we don't have to worry about trying to find a specific amount of free space. There's someone at the back that's had his hand up for a while, so I want to ask him. Can you repeat your question, please? Sectors, yes. So we're going to come back to drives later in the course. Sectors for us, as far as we're concerned right now, is that a sector is another smaller unit than block usually, but functionally and conceptually they're the same idea. It's a fixed size thing. The thing that we're going to be able to use as an assumption later is that writing an entire sector is an atomic operation. So I think you were the one asking about atomicity and atomic before. So this idea is basically like, we can guarantee that this entire sector was written or it was not written, but it's never going to be half written. And we're going to use that when we get to thinking about journaling to make sure that our file system stays in a consistent state. Yeah. Okay, yeah. In the metadata, can we define the block size? In practice with real file systems, there are, so like ext4 and I think BetterFS can do this. You can have different regions in the data region that have different block sizes. But with BSFS, we just have something it's a very simple file system. So we just have one fixed size block for the whole thing. So with a real file system, you could say, this is a giant file that I'm going to write. So put it in this region that has really big blocks. Or this is a really small file, so put it in the region that has really small blocks so that you're not wasting too much space. I'm not sure if any of them support having like multiple sizes of blocks for one single file, but I know that they can support for at least one file that can have a block size. Yeah. All right, cool. This is a great discussion. Thank you all for asking these questions. Like I said, I hope that this idea of direct and indirect block pointers is clarified compared to what's in the textbook in terms of how this overall structure works. The idea of double indirect and then triple indirect block pointers is the same sort of idea, where you've got a triple indirect block pointer points at blocks that are double indirect block pointers. Those all point at indirect block pointers, and those all point at block pointers. This structure that we're looking at right now turns into a tree. This whole inode structure turns into a tree, not a file system tree, but like a tree of pointers to things. And it's super, super off balance. The direct block pointers, there's a small number of them. Indirect block pointers, there's many of them. Doubly indirect block pointers, there's many, many more of those. And triply indirect block pointers, there's many, many more of those. This is a whole tree structure for just one individual file to have all these block pointer structures. All right, so what I would like to do now, I'll post this diagram up for you on the course webpage so you've got a copy of that. What I'd like to do now is scoot back over here to my slides, and I'd like to spend some time taking a look at a real file system. The way that I want to do this is I would like to run some commands on the command line. I want to make a new ext2 file system. I want to put this file system in a file on the command line, and then I want to inspect that file system using a program that's called hexdump. Hexdump is going to print out the contents of a binary file as a hexadecimal file, and it will also conveniently for us show like ASCII representations of the data on the side of it. Then what I want to do is try to do something a lot more limited in C. I want to get us started with the same actions that we're doing in hexdump in C. So in hexdump, what we're going to be doing is like navigating around this file. And then we're going to be looking at values in the file to decide where to go next and how to calculate those values. And then we're going to start to do those things in C, but I'm not going to go through the same depth. I'm not going to go to exactly the same depth. I'm going to give you the things that you should be able to complete doing this task with. I invite you to follow along with me. So I've posted up a skeleton of this entire thing up on GitLab here. This is on code.cs.umanitoba.ca. I'm going to clone this into my aviary account. You're welcome to clone this onto your aviary account as well. And then you can follow along with me as we're going through this. So I'm going to pop over, I'm going to open a new terminal here, and I'm going to connect to aviary. And then what I'm going to do is I'm going to remove this old copy of the files that I was working with, and I'm going to clone this thing again so that you can get a sense of what I'm doing here. Is that text big enough for you at the back to see? Yeah? Okay, awesome. So I'm going to clone https ://code.cs.umanitoba.ca comp 3430 winter 2025, and then it's called ext2 inspect. What I want to do with this, I'm going to change into this directory. I'm going to list the contents here. And what I have got is a README file. I'm not going to open this because these are basically some of the steps that we're going to go through right now. But I wanted to document them for you so you could get started with this again quickly if you wanted to try. There's a skeleton C file that we're going to look at shortly that will do some of the stuff that we're going to be doing on the command line. We're going to use this as a starting point for this. There's a directory here that's called ext2 files. And ext2 files, what it has in it is a README. And the contents of the README are this. The goal that I have for us is I want to make a new file that has an ext2 file system in it that includes this file in the root directory. So the root directory on a file system on a Linux or a Mac machine is like // This is the root directory of that file system. On a Windows machine, it's kind of like C:\\. This is the root of a drive. This is the folder that has the kind of main entries for the stuff that we're looking at. So the very first thing that I want to do here is I want to make a new file. I'm going to use a program that's called truncate to do that for me. Truncate is a program that will just make an empty file of a specified size. It doesn't have anything in it. So I'm going to say truncate. I have to tell it what size I want it to be. I want this to be a really small file. I don't want to have like hundreds of megabytes of data on my aviary folder. I just want something really small that we can actually work with. So I'm going to make this a 256 kilobyte size file. And I'm going to call this ext2 volume. There's a question on the course forum about what the word volume means. Volume here means basically like this is a thing that contains a file system. That's effectively what we need to think about this as right now. Sometimes it's a whole hard drive, sometimes it's just part of a hard drive, but it's a thing that contains a file system. That's how we're going to imagine this idea. So if I do ls-lh in my directory right now, there's this new file that's called ext2 volume, and it is 256 kilobytes in size. And if I use a program that's called hex dump, I'm going to say hex dump -v. -v says don't skip 0 lines. There's going to be a lot of data in here that has nothing in it. In fact, it's all zeros right now. So I want to actually see that. I don't want you to just skip all of it. And then -c, uppercase C, is for canonical mode. So it's going to print out the address in a column, the actual data as 1 byte values. So there's 2 hex values right beside each other. It's going to put 16 bytes per line, and then it's going to put an ASCII representation of those bytes in a little table beside it. So I'm going to say ext2 volume here, and I'm going to pipe this to less. I don't want to just hit enter here because this is going to print out a ton of lines immediately because it's just 256K of zeros. So if I hit enter here, it is what it says on the box. It's an empty file that has nothing in it, just lots of nothing right now. So I'm going to quit this. The next thing that I want to do is I want to use a program to make a file system in this file. On Linux, a lot of the file system creation commands start with the letters MKFS, so makefs, make file system. The ext family of makefs commands are like dot, so makefs dot, and then you can do ext2, 3, or 4 if you wanted to try making these different file systems, but I want to start with ext2. There's a bunch of options on this command that I invite you to read the manual page if you want to see more about what these options are. I'm just going to tell you these options that I'm using right now. The first one is a D option, and I want to pass ext2 files to that. D says, I want you to take the files that are in this directory, and I want you to drop them into the root folder of this file system. So this is going to copy data into the file system for us. Then what I want to say is I want to give my file system volume a label. So uppercase L is make a label for this. The labels for ext2 are limited to 16 characters, so I'm going to make this comp3430-W25. The dash uppercase I option specifies the size of an inode. The default right now for all ext file systems is that inodes are 256 bytes in size, but I don't want 256 byte inodes. I want 128 byte inodes, so I'm going to say 128 here to say that you should make 128 byte inodes. The last thing that I'm going to pass to this is my volume name here to tell it what file to make the file system in. So the wording that we see coming out of this on the first line below make E2FS is 128 byte inodes cannot handle dates beyond 2038 and are deprecated. The default is 256 bytes, but just for the sake of this example, I want to use 128 byte inodes so that I know what their size is. And it also just makes things a little bit easier for us. What it also tells us here is that it's created a file system that has 64 4 kilobyte blocks and 32 total inodes. So that means that we're going to be able to represent at most 32 files in this file system, and in practice less because some of the inodes are reserved for other things like the root directory. So it's not really a practical file system, but it gives us something to try out and to take a look at. So now what I'm going to do is I'm going to hit up on my keyboard here. I'm going to do hex dump one more time. And what I'm going to see here is still lots of nothing, but that's actually kind of expected. What I'm going to do is I'm going to bring my terminal over to the side here, and I'm going to put my web browser over on the other side here. I'm going to make this just a little bit smaller. Is that still okay to see at the back? Okay, awesome. I'm going to make this one just a little bit bigger. Is that okay to see at the back? Okay, awesome. This page that you see on the left of my screen, this is something that I've posted as a link to the course webpage, so it's up there already. You can take a look at this. There's another one that's called the OS Dev Wiki that has the same information, but I'm using this file to start with. This is a document that describes in comprehensive detail the structure of an ext2 file system. It tells us about how many bytes each of the properties of an inode is, so that we can do things like navigate around the file system to find different stuff. So what I'm going to do here is I'm going to click on the superblock link. Just to be clear, the overall structure of ext2 in terms of like the layout that you saw in the textbook, it's basically the same structure. There's a superblock at the beginning, although it kind of doesn't really look like a superblock here. It's just a bunch of zeros. There is a superblock at the beginning, but what we can see here is that the superblock is always located at byte offset 1024 from the beginning of the file, block, device, or partition formatted with ext2 and later variants. So what this is saying is that in order to be able to find this superblock, we can't just look at the first bytes of the file. We have to go to the first 1K of the file to begin finding the superblock. Hex dump here is printing everything out in hexadecimal addresses. So I'm going to have to go back and forth between hex and decimal here to do that. But I can't do that stuff in my head, so I like to have a calculator with me. And what I'm going to do is I'm going to type in 1024 here. And what that's showing me here in my calculator is that this is 400 in base 16. So in hexdump, I can do a search in this file using / on my keyboard. And you can see right here that it's done a little / here. This is kind of the same as Vim. It's kind of the same as less in terms of searching for stuff. So if I go to location 400 here, now we can see stuff. And there's some stuff that you can immediately see about this file system. One of those things that I immediately see is this, comp3430W25. This is the label that we specified for this file system on the command line. The other stuff that we can begin to see here is in this table here, table 3.3, this is the superblock structure. This is the byte layout of all the different properties that we have in this superblock structure. So the first 4 bytes of the superblock here is a property that's called inodes count. So here, the first 4 bytes here are these 4 bytes. Hexdump here is printing this out as little endian. So that first byte is the least significant one. So 20 here, this is a hex value 20. If I go back to my calculator here and I switch to hex and I type in 20, the value that we're getting in base 10 here is 32. There are 32 inodes, which is what makefs.ext2 told us when we asked it to make this file system for us. There's other stuff in here like blocks count, blocks count. So blocks count is how many total blocks there are. Free blocks and inodes count. These are the total number of blocks and inodes that are not used. These are not the actual allocation structures. This is just a quick check. How many inodes are currently free in total? How many blocks are currently free in total? There's another value way down here at byte 56 in the file that's called magic. This is a property that always has a well-known value. So on an ext2 formatted file system, this value will always be 0xEF53. So this is a hex value. It's always going to be EF53. So at byte 56, in this file system, we should be able to find that EF53 value. I'm going to go back here, and what I want to do next is now that we've got the superblock here, what I want to do is I want to start taking a look at the inode table. In ext2, our superblock doesn't actually say, our superblock itself doesn't have a pointer to where the inode table is. In some file systems, this superblock or this place where there's metadata about the file system will say, like, this is where you have to go to find this thing. But with ext2, it's not in the superblock. I'm actually going to go to a different location in this file, and I'm going to go to this block group descriptor table. The block group descriptor table is going to be like a small, tiny file system that has its own allocation structures and data blocks. So with VSFS, when we were looking at that structure, we kind of saw like there's a superblock, allocation structures, an inode table, and then data blocks. With ext2, it kind of does the same thing. There's a superblock, and then there's block groups. And a block group consists of allocation structures and an inode table and then data blocks. But there might be many block groups in the file system as opposed to just one like what we saw in VSFS. What this table tells us, what this description tells us is the block group descriptor table starts at the first block following the superblock. The block size for this file system that we just made is 4 kilobytes. The superblock itself, I'm going to go back to my superblock here. The superblock itself, if I look way down here, is 264 plus 760 bytes in size, which is about 1024K. It's exactly 1024K. It's exactly 1024K, and it starts at 1024 bytes, sorry. It's 1024 bytes, and it starts at 1024 bytes after the beginning of the file system. So our superblock ends at 2K. So it ends in the middle of a block. So this block group descriptor table then starts at the next block after the superblock, which means that this just starts at block number 1 in our file system. Block number 1 in our file system is at 4096 bytes, so 4K. I can't do this base 10 to 16 calculation in my head. So I'm going back to my calculator, and 4096 is at location 1000 in hex. So I'm going to pop back here, I'm going to search for location 1000. And what we see here is some information about this block group descriptor table. The very first byte that we have here, the very first 4 bytes that we have here, these are going to be a pointer to the block bitmap for this block group. So these 4 bytes here, what they're saying is data block number 2 is the block bitmap for this one. These next 4 bytes here say that this is the inode bitmap. And these next 4 bytes here say that this is the inode table. And the inode table is kind of where I want to go next. I want to find out where stuff is in the inode table. So I'm going to go to the inode table, and this starts at block 4. This is data block 4. So I'm going to go back to my calculator again. I'm going to multiply this by 4. So 4096 is my block size, and I want to go to the 4th block in from this. And this is at location 4000. That kind of makes like arithmetic convenient here, is that I could have just multiplied it by 4. So I'm going to go to block 4000 here. And there's more bytes, there's more data here. What I'm going to do is I'm going to click on this link, because it's going to take me to description of the inode table itself. When we made the file system, we said inodes are 128 bytes in size. And that's the same size as the structure that we have here. And what we can see with this structure is that we've got things like mode. This is the permissions of the file. So the very first thing in my inode table here has a bunch of zeros for permissions. So there's no permissions on whatever this first thing is at all. There's a UID. This is the person or user account that created it. This is the next 2 bytes. UID 0 typically means root. This is the administrative user of the system that's made this file, that's made this inode. The next 4 bytes here are for size. So this is an inode that has 0 bytes for a file size. This is a weird looking inode immediately. Then there's things like A time, C time, and M time, and these are all 4-byte values. I can't parse out these bytes to represent what their actual time is, but you can click on this description if you want to. The important thing here is that the first few entries of the inode table are reserved. And the other important thing here is that the first inode is inode number 1. It's not inode 0. This is not a 0-based array of inodes. This is not a 0-based array of inodes. This is not a 0-based array of inodes. This is a 1-based array of inodes. The first inode is inode number 1. So this inode that we're looking at that has 0 bytes and no permissions and was created by root, this is inode number 1, and it's something that's called the bad blocks inode. This is metadata that our operating system and our file system can use to keep track of parts of the disk that are not usable anymore. This is not so relevant anymore, but it used to be the case that hard drives failed a lot. They failed a lot, but only parts of them, and they were also super expensive. And so if only a couple of blocks were bad on a 20 meg hard drive, you didn't want to throw the whole hard drive away because it would cost $1,000 to buy another one. So you just wouldn't use those blocks anymore. You just use the rest of the disk. So this is the first one. The second one here, this is the one that we actually care about. And now this is a well-known location. This one says that inode number 2 is the root directory inode. So inode number 2 is going to start at 128 bytes after the beginning of this table. Each inode is a total of 128 bytes in size. Inode number 1 starts at 0 bytes offset. Inode number 2 starts at 128 bytes offset. 128 bytes offset, and I'm going to calculate this way. We're going to say that this is the beginning of our inode table. And I want to add to this 128 bytes. This is the total size of each inode. And I want to multiply this by inode number 2 minus 1. Inode number 2, but this is a 1-based array. So the first inode is inode number 1, but it's at location 0 in our array. So that says that our root directory here is going to be at location 4080. So if I go here, here's 4080, and we can now start to see that, okay, there's actually permissions on this file. It was created by the root user. It has a size here of 10, so 1000. It has a size of 1000, which is going to be a directory size that we've got. But then the really important part that I want to actually get to here is iBlocks. iBlocks, these are our direct pointers. These are the pointers that say, this is where in the file system the data is for this inode. So that's going to be at the next offset here, which is at 28 bytes after the start of this inode. So I'm going to go back to my calculator here. I'm going to add to this 28 bytes. And this takes us to 409C. 409C is going to be somewhere around here. And what we can see here is that the first data block for this is at block number 3. That's not the right one, sorry. It's down here. It's block number 5. This is the first block pointer for this inode structure. So what I want to do now is I want to go to block number 5. And the way I'm going to do that is I'm going to go back up to my calculator here, 4096 times 5, and that takes us to 5,000. So again, I could just do this in my head if I could think this way, but I just can't think this way. So I want to go to 5,000 here. And at 5,000, there's some readable stuff there. So we have two things that are there. There's this lost plus found, and then there's readme.md. This now is a set of directory entries for the directory that we're looking at right now. And remember that directory entries here are what actually contain the file names, and then the inodes that the file names refer to. We've only got about 30 seconds left. So what I'm going to do here is I'm going to just skip ahead a little bit. And I'm going to say that we're ultimately going to get to location B1000. And B1000 is where the actual data for this file is. I'll do this on Monday's class so that we can actually see how I got here from that root directory entry. And then what we're going to do after that on Monday is we'll start taking a look at some of the stuff in C. So what I'd like to finish up here with is you should be able to start doing the show common file operations are performed in terms of manipulating a file system's data structures. So this is read. We're not manipulating anything right now, but we've gone through the process of finding the super block, and then finding the inode table, and then finding the inode for the root directory, and then finding the directory entries for the root directory. And now we're going to start after that finding where the inodes are for the actual files from these directory entries. That's it for today. I hope that you all have a great weekend. Stay safe when you're going home, please. You know, it's blizzardy out there. And yeah, have a good weekend. Bye, everybody.